So there's no dependence either on energy or on angle. Yes, sorry.
No, I mean, so it could be, theoretically speaking, in principle, it should be possible that, you emit two particles, but they go in the opposite direction and maybe with different velocities, and that would still conserve the momentum.
Except because the particles are massless, they have to move at the speed of light. That's the point. Because they're massless, they're always moving at the speed of light, and so this is where relativity plays an important role, and that's why I say this is dictated by the principles of space-time. But you see, what's really cool is it can't depend on energy or angle, and therefore it's completely fixed by up to overall strength of the interaction, the number that goes with it. It's completely fixed just by giving the spins or the helicities of the particle. There's no other data that it can depend on. Okay, now, so once you take that, now we can go back to the four-particle process, and now there's actually an important constraint on four-particle scattering, which is that when the energies of the two incoming particles A and B are such that they could actually produce a real intermediate particle E, then we should have a resonance. Okay? And this is a very familiar phenomenon of resonance, that when you excite a system at at one of its natural frequencies, the amplitude becomes large. So here we should expect that if particles A and B satisfy that the momentum, the energies and momentum of A and B can add up to some E in the middle, the amplitude should blow up. But how it blows up should be dictated by the product. You should interpret that blow up. This is the principles of quantum mechanics now. Quantum mechanics tells you should be able to interpret that blow up as actually producing particle E, and then having particle E travel some distance and decay to C and D. So this is a mathematical constraint on this function. This function can have poles, can have singularities, in the simplest case can have poles, but the residues on those poles have to factorize into the product of these two simpler amplitudes. And remember, I just told you by the principles of space-time that these amplitudes are actually completely determined up to the strength of the interaction. So this is an interesting mathematical constraint. You have to write down some function of energies and angle with poles which factorize properly on the poles in this way. And now all you have to do is solve this mathematical problem, and it's a very simple problem to solve once you have the right very simple formalism. In about a year of grad school and about half a page of algebra, or maybe 1.5 pages of algebra, depending on how big you write, you discover the following amazing thing, which is that the only possible solution to that consistency condition involving four-particle scattering tells you that you can't have any old spins. The only particles you can have spins 0, 1/2, 1, 3/2, and 2. Okay, and so therefore, just the laws of relativity and quantum mechanics have reduced all the complexity of the world down to just choosing a menu of these guys and the strength of their interactions, and that's it. And as I mentioned before, the spin 2 guy is unique. You discover you can't have more than one of them. You can have only one of them, and their interactions are universal. They have universal strength coupling to everyone. It's gravity, but you discover that as just one of the solutions of this, of this simple mathematical consistency condition that incorporates in the most direct way the principles of space-time and quantum mechanics. You discover you can have particles, massless particles of spin 3/2, but remarkably, you can have at most 8 of them. And I'll come back to say a little bit about this in a moment. You can have particles of spin 1, but the interactions they have to have the famous Yang-Mills structure. But it has nothing to do with the beauty of group theory and symmetries and so on. It's just one of the solutions to this beautiful little problem of consistency of relativity in quantum mechanics. Similarly, you can have any number of these particles of spin 1/2 you want. If there are spin 1 guys around, they have to interact with them in a particular way. Similarly with all the higher spins. And spin 0. I've put in red 0 and 3/2 the spins that are not those of familiar elementary particles. We'll come back to the spin 0 in a second. But remember, electrons and so on have spin 1/2, photons and W's and gravitons have spin 1, and photons and gluons and so on have spin 1. The graviton has spin 2. All right, so what I've told you is that, again, the sort of grand architecture of the laws of physics are basically determined by the principles of space-time and quantum mechanics. There is one footnote, which is about the story of the Higgs particle. And the footnote is that at the very start of the discussion, I said that, well, when we go to very high energies, we should be able to ignore the masses of the elementary particles. But there's actually, that's not as innocent as it seems. You can't be a little bit massive. It's like being a little bit pregnant. And that's because of this amazing difference between massive and massless particles with spin. Let's say you have a massive particle of spin 1, like the W particle. What that means is no matter how fast it's moving, I can always go to a frame to catch up with it. And if I catch up with it and I see it spinning up, by tilting my head, I can see it spinning in all 3 directions. So rotational invariance tells me that a spin 1 particle has to have 3 possible ways that it can spin, 3 spin degrees of freedom. On the other hand, a massless particle, I can never catch up with it. And therefore, I can never decide, I can never do this tilting my head to see it spinning in all possible ways. And that's why massless particles only have 2 spin degrees of freedom, not 3. Okay, so there's one extra guy. If you have particles with spin, there's really one extra guy degree of freedom associated. And so when we go to very high energies, we have to keep track of that. In fact, if you imagine a massive spin 1 particle like the W particle that we had talked about, and imagine that it's spinning in some direction orthogonal to the way that we'll eventually boost it, then it's sort of intuitive that the amplitude to find it spinning in these orthogonal directions should not depend on how much I boost it. But again, by a dimensional analysis, if it's spinning in the direction in which you boost it, the amplitude to find it in that state does grow, and it can grow like the energy divided by the mass of the particle. So this is the new extra guy that we have when we go to very high energies. And we see that the kind of the possibility of it spinning in the longitudinal direction, the direction of its motion, means that even if the basic coupling constants are dimensionless, because of this sort of kinematic fact that the amplitudes involving the longitudinal components might still grow. And in fact, this is exactly what happens if we take the scattering between these W particles. The amplitude between the normal guys that have like helicity, the ones that would be there if it was just massless, their amplitude has the same q squared in it, which is about 1%. But the amplitude for the longitudinal guys, they still have the q squared from these couplings, but they have this kinematic piece that grows like the energy over the mass squared. And so even though this number is around 1%, when the energy over mass becomes around 10, the amplitude becomes of order 1 again, and something bad has happened. Again, we have the same problem. When an amplitude is of order 1, the probabilities are threatened to be bigger than 1. Something new has to happen. And the mass of the W particle is around 80 GeV, 80 times the mass of the proton. And if you put the numbers in a little bit of detail, something new has to happen when the energies are around beneath around 1200 GeV. And so from the first part, just by units, you might have thought that the story was that we have all the particles that we've seen, we go to very high energies, we can ignore their masses, and then maybe something very new is happening near the Planck scale, 10 to the 19 GeV. But in fact, that's a naive expectation if we could just ignore masses because we go to high energies. But the actual situation is that something new had to happen beneath around 1000 GeV that was much, much closer to home, okay, way before we get there. And what is that new thing? Well, you need something new. Some other thing has to come in order to solve this problem. And what's the menu of possibilities you can have for this new thing? Well, it has to interfere. It has to add to these processes that we talked about and fix this issue up somehow. We go through the menu of possibilities for what it could be, and you can definitely cross out all the possibilities of spin 2, 3, 4, and above. Spin 1 was maybe a possibility for a while, but it had other detailed problems. So the only thing and the simplest thing that could be is just a particle of spin 0, and that's the Higgs particle. Okay, So that's the story of the Higgs, is that we needed something to allow us to be able to interpolate between the world of massive particles at very low energies and this very rigid set of theories for massless particles at high energies. And just the degree of freedom counting did not work. If we just took the massive particles that we knew, we couldn't reassemble them into these consistently interacting massless theories at very high energies unless we added something. The amazing thing is that all it took was a single degree of freedom. One elementary particle was all it took in order to allow this to happen. And at very high energies, this extra Higgs particle, together with these additional longitudinal components of the W and the Z particles, unite into objects that have exactly the allowed kind of interactions for massless particles. Okay? So finally, with the Higgs, we have in our hands a theory that we can extrapolate to much exponentially higher energies without running into any internal theoretical inconsistency. Now, the only place we run into a theoretical inconsistency is when we go all the way up to the Planck scale, where, as I mentioned before, now we have those problems involving the gravitational amplitudes becoming large. And so the story of the Higgs is really a sort of a triumph for this theoretical structure, because you look at the menu of possibilities of what you're allowed to do. You're only allowed to choose from this menu of particles of spin 0, 1/2, 1/3, and 2. And the thing with spin 0 actually solved this theoretical problem of the interpolation between massive particles at low energies and massless at high energies. And famously, 10 years ago, on July 4th, 2012, the Higgs particle was discovered at the Large Hadron Collider, where protons are collided at 0.9999999 times the speed of light, probing distances around 1,000 times smaller than the nucleus of the atom. And I won't explain this plot, but there it is. It was a triumph for experiment, a triumph for theory, and an indication that these basic fundamental principles of space-time and quantum mechanics works. And that's why the Higgs is such an exciting particle. It's really the first really new elementary particle we've seen. It's the first example of the simplest possible elementary particle of spin 0 that we've seen before. And even though I'm running very short on time, I hope I'll get to say a little bit about it. That very simplicity is what makes it so perplexing at the same time. So now we've turned this red into black. We've now seen nature make use of this possibility as well. Now the only thing that we've not yet seen nature make use of is the possibility of elementary particles of spin 3/2. That has to do with the notion of supersymmetry, and I'll come back to that again if I have time in a little bit.